All right, let's jump right in. I want you to consider a pretty wild idea for a second. What if the most complicated things you can imagine, we're talking everything from how galaxies form to how your own mind works, what if they all follow the exact same, simple set of rules? Today, we're going to unpack this incredible universal blueprint. You know, when you look across all of science, you see this pattern over and over again. Things come into being, they find a way to become stable, and then eventually they change. But what if there's a hidden architecture behind it all? Is there some kind of universal rule book for how complexity gets its act together? So, that's the big mystery we're tackling, and it's a huge one. This question stretches all the way from the very first moments of the universe right down to the thoughts that are literally forming in your head this very second. Let's start big. I mean, really big. Think about galaxies. Over billions and billions of years, a whole lot of cosmic dust and gas somehow manages to organize itself into these magnificent, stable structures that we see in the night sky. Okay, now let's pull the camera way, way back, all the way down to biology. On this scale, you've got individual cells that are all interacting, forming tissues and organs, and eventually creating entire living things that hold a stable shape. And we can zoom in even further, right into our own heads, to the world of cognition. Somehow, all these fleeting, chaotic neural firings inside our brains create incredibly stable patterns, things we call memories or skills. So what's the deal? How do all these completely different systems manage to achieve this kind of stability? Well, the answer starts with this really powerful concept, a key idea for how these systems manage to hold themselves together. It's basically a kind of self-stabilizing loop. The technical term is constraint closure. I know, it's a bit of a mouthful, but the idea is actually pretty simple. You see the circle logic, right? A system basically creates its own set of rules, its own constraints, and then those very same rules turn around and keep the system in line. It's a completely self-creating, self-maintaining machine. Now you might be thinking, oh, that's just a simple feedback loop, like a thermostat kicking the furnace on. But this is so much more sophisticated. We're not talking about one part directly controlling another. We're talking about the entire network of components working together to create this massive collective system that regulates itself from the inside out. Okay, so if that's the what about the how? How in the world do these self-stabilizing loops even get started? Well, researchers have come up with this fascinating three-level model to explain it, and it's called the CRET model. And here's what it looks like. It all starts at the bottom, with what they call micro-level interactions, just tiny little events. But when enough of those happen, they start to build up into these meso-level networks in the middle. And here's the magic trick. Once those networks get dense and organized enough, they support this big, stable, macro-level regime at the top. That macro regime could be a galaxy, heart tissue, or even a memory. But for this whole thing to work, two absolutely crucial things have to happen. First, that middle layer, the network, it has to hit what's called a critical density. Think about a rumor spreading online. It goes nowhere until enough people are connected. It's the same idea. Second, the feedback from that top layer all the way back down to the bottom has to be powerful enough to keep the whole cycle going by itself. And believe it or not, you can boil that second point down to this super simple formula. The feedback strength, or gain, that's the G, it has to be greater than or equal to 1. If it's less than 1, the system just fizzles out and falls apart. But if it hits 1 or goes above it, the system locks in. It becomes self-sustaining, it's officially stable. And now this is where things get really, really powerful. Because this same model, this same set of rules, can be applied to a shocking range of things. Let's take a quick tour and see how it works in some totally different fields. Let's go back to cosmology. The micro-interaction is just gravity pulling little bits of matter together. Once you get a critical density of that matter, the feedback loop gets strong enough. That G value clicks past 1 and boom, a stable galaxy is born out of a simple cloud of dust. How about in biology? Here, the micro-interactions are things like genes turning on and off or cells sending signals to each other. They create these incredibly dense networks, they lock into a stable state, and suddenly you have the macro regime we call a liver, or a heart, or a lung. This model even reframes how we think about disease. Take cancer. We tend to think of it as just pure chaos, but really it's the emergence of a new, but pathological, stable system. Something from the outside disrupts the healthy tissue stability, and that opens the door for a new tumor regime to form its own self-stabilizing network. It's literally a battle between two competing stable systems. Okay, so we've got a handle on stability. These systems are really good at maintaining themselves. But that begs the question, right? If they're so stable, how does anything ever actually change? How do they ever break out and become something new? Well, it turns out change isn't spontaneous. It needs an external push, a perturbation. This nudge doesn't necessarily destroy the system, but it can weaken its stability just enough to open what scientists call a metastable window. This is a temporary, fragile moment where the old rules are weakened and reorganization is actually possible. And what's absolutely amazing is that we can often see this coming. As the system gets closer and closer to a tipping point, it starts to send out these early warning signals. For instance, it shows critical slowing down, which just means it takes a lot longer to recover from small bumps. Think of a spinning top that's starting to wobble. Its behavior also gets more erratic. It fluctuates more wildly. Because we can spot these signs, this theory actually becomes predictive. So, when you put all of these pieces together, you realize it's not just a theory about one particular thing. It's like getting a new pair of glasses. It's a whole new lens for looking at pretty much any complex system you can imagine. This quote from the research paper says it all. This pattern, this structural recurrence, just keeps showing up everywhere. This fundamental dance of interaction, constraint, and feedback might just be the general mechanism for how everything organizes itself, from stars to societies. And look, this isn't just an abstract idea for a classroom. It has huge practical implications. It means we could potentially predict when an ecosystem is on the verge of collapse and actually have a chance to intervene. We could learn exactly when and how to nudge a system toward a better state. And as we talked about, it gives us a powerful new way to think about disease, not just attacking symptoms, but finding clever ways to disrupt the very stability that keeps the illness locked in place. This framework gives us a brand new way to see the world around us, from our societies all the way down to our own health. So it leaves us with a really fascinating question to think about. Using this new lens, what complex system in your world, in your job, your community, or maybe even your own life, do you think is starting to wobble?